Welcome back. So picture this. You're standing right in the middle of a river of data. We're talking a continuous, never-ending stream of integers just flying past you. Think real-time financial ticks or live sensor data. Our challenge for this explainer is hunting down a moving target. We need to explain the coding problem median of an integer stream and figure out how to find that exact middle value at any given second. We're going to explore how to design a data structure that can catch these new numbers and instantly spit out the median without breaking a sweat. It's absolutely brilliant, and it's a perfect lesson in using exactly the right tools for the right job. Let's get into it.
Okay, let's look at our roadmap. First, the core friction of the median problem. Then, the two heaps intuition. After that, we'll go over populating and balancing these heaps, retrieving the median, and finally, the implementation and complexity.
Section 1. The median problem.
Right, so here is the core dilemma we're facing. By definition, a median implies order, right? It's the exact middle value of a sorted list. But in a fast-moving stream, these numbers are arriving completely out of order. Now, if you've worked with data structures, your very first instinct might be, well, just sort the list every single time a new number drops in. But think about the computational cost there. Constantly resorting an ever-growing array, that is a massive bottleneck. It's computationally impossible to sustain efficiently. So we're going to need a completely different approach.
To figure this out, let's just ground ourselves for a second with a simple static array. When the data is perfectly still and sorted, finding the median is a piece of cake. Here, our middle values are 3 and 4. Now, the stream obviously isn't static, but this actually hints at our ultimate goal. We don't actually care if the 0, 1, and 2 or the 5, 7, 8, and 9 are perfectly sorted amongst themselves. We literally only care about isolating those central values.
Section 2. The two heaps intuition. And this is where we get our massive paradigm shift. What if we split the data into a left half of smaller numbers and a right half of larger numbers? The two values we need for the median are right there at the boundary. The first median is just the largest value in the left half, and the second median is the smallest value in the right half. That's the whole secret. We do not need a fully sorted list. We just need a way to efficiently pull the maximum of one group and the minimum of another. And hey, if we have an odd number of elements, we just grab the largest value from the left group. To do this super fast, we use heaps, a max heap for the left side and a min heap for the right.
Section 3. Populating and balancing heaps.
So these two heaps basically act like a balancing seesaw, and they're bound by a very strict contract. We've got two non-negotiable rules. Rule 1. Every single value in the left half has to be less than or equal to any value in the right half. The top of the left max heap can never, ever exceed the top of the right min heap. Rule 2. The heaps have to maintain roughly equal sizes. They can be exactly equal, or if we're dealing with an odd total number of elements, that left max heap is allowed to hold exactly one extra element.
Let's picture a perfectly stable, balanced state. Our left max heap might have 5 elements, and its maximum value is sitting right at the top, the number 4. The right min heap has 4 elements, with its minimum value at the top, the number 5. Rule 1 is completely intact because 4 is less than 5. And Rule 2 is intact because the left side has exactly one more element than the right. Total harmony.
But wait, the stream never stops. Suddenly, a wild number 3 appears. Now, because 3 is less than our left heap's maximum of 4, it rightfully belongs in that left half, so we drop it in. But take a look at what just happened to our sizes. The left heap now has 6 elements. The right heap has 4. The difference is 2. Our balancing scale just violently tipped to the left, and we've totally violated our second rule.
Now, what's really brilliant here is how we fix this imbalance without having to resort the whole thing. We just shift the weight. We take the top element from that overloaded left heap, the 4, and we just toss it over to the right min heap. Boom! Instantly, the left heap settles back down to a size of 5, with its new max being 3. The right heap grows to a size of 5, and its new min is 4. The rules are restored, and our heaps are perfectly primed to hand us the median again.
So this gives us a standardized, logical rule for the algorithm. Anytime we add a number and the left half becomes too large, meaning its size beats the right half by more than 1, we execute this exact rebalancing maneuver. We pop the top value off the left half and push it straight onto the right half.
And the exact inverse is true as well. What happens if a huge flood of large numbers comes in and the right half gets larger than the left half? Remember that rule. They need to be equal, or the left can have one extra. So if the right side ever gets bigger, even by just one single element, we pop the top of the right half and push it right back over to the left half. This super strict discipline guarantees that the median values are always sitting right at the top of the heaps, just waiting for us.
Section 4.
retrieving the median.
When it comes time to actually grab the median, it all boils down to whether we have an even or odd total number of elements. If the total is even, it means our two heaps are exactly the same size. So we simply pluck the top value from the left heap, grab the top value from the right heap, add them together, and divide by 2. Easy. Now, if the total is odd, we already know based on our structural design that the left heap is holding that one extra element, so the median is just sitting there, right at the top of the left heap. We grab it, and we are done. Literally 0 calculation required.
Section 5. Implementation and complexity.
I've got to share a really fun little implementation quirk here, especially for the Python devs tuning in. Python's standard library actually comes with a built-in heap queue, but it only creates min heaps by default. There is literally no built-in max heap. So engineers use this very clever, kind of funny hack. To mimic a max heap for our left half, we take the incoming number and just multiply it by -1 before we insert it. By negating the values, the largest original value suddenly becomes the smallest, which naturally floats to the top of the min heap. And when we need to retrieve it, we just multiply by -1 again to flip it back. It is a brilliant, highly effective workaround for sure.
Okay, the big O payoff. Adding a number to our structure only takes O of log n time, because inserting into a heap and potentially popping it over to the other heap to balance, those are logarithmic operations. But retrieving the median, grabbing the exact middle of a massive, endless stream of data, that is O of 1. It is instantaneous. It takes constant time because we're only ever looking at the very top of our heaps. Our space complexity is O of n, since we naturally have to store the n elements flowing into the stream, but honestly, this performance profile is just spectacular.
Before we wrap up, here's a quick semantic thought for you to ponder. Technically, a dataset only ever has one true median. When we're looking at an even number of elements, those two middle numbers we grab are really just the components used to calculate that single central point. It's a fascinating little mathematical nuance to think about, especially now that you've totally unraveled how to track that moving target in a continuous stream. So what other impossible-sounding data problems can we solve by just shifting our perspective? Thanks for joining me on this explainer. I'll catch you in the next one.